In April 2025, China stunned the world with the test of a non-nuclear hydrogen bomb, using 4.4 pounds of magnesium hydride MgH₂ to create a blazing fireball that reached temperatures of more than 1,800 degrees Fahrenheit and burned for over 2 seconds. Its thermal power was 15 times greater than TNT, marking a new era for advanced material technology. This solid hydrogen storage breakthrough is not only a scientific milestone, but also promises a wide range of applications, from precision military systems to clean energy storage for civilian use. Join Top 10 Discoveries Official as we explore how China achieved this feat and what it means for the future. The research and development journey of magnesium hydride technology in China began with early efforts to solve the challenge of storing hydrogen safely and efficiently. From 2010 to 2018, scientists at the Dalian Institute of Chemical Physics under the Chinese Academy of Sciences focused on fundamental experiments, using nanocatalysts to improve the speed of magnesium hydrogenation. They achieved preliminary results at a small laboratory scale, producing only a few grams per day. These studies primarily explored the chemical properties of MgH₂, such as its hydrogen storage capacity by weight of up to 7.66%, making this material a strong candidate for future energy applications. During the period from 2019 to 2023, close collaboration between the Dalian Institute of Chemical Physics and the Ship Research Institute No. 705 under the China State Shipbuilding Corporation accelerated progress. This led to the completion of a one-pot synthesis method in 2022, allowing for more stable MgH₂ production without complex intermediate steps. As a result, laboratory output gradually increased, reaching several ounces per day in the final trial batches. While significantly reducing the energy required for decomposition, the research teams also integrated catalysts such as niobium oxide to enhance material durability, expanding potential applications from energy storage to controlled detonation systems. By 2024 to 2025, the project moved into large-scale trials, with outdoor explosions carried out at specialized test sites in Shanxi, culminating in the successful experiment on April 21st, 2025. Throughout this journey, major challenges such as the high reactivity of MgH₂ with humid air were overcome with vacuum environment control systems and advanced protective coatings, ensuring safety in production and storage. Total investment in the research exceeded $210 million, with more than 600 experts across chemistry, physics, and engineering involved. This reflects China's strong commitment to leading advancements in material technology. The magnesium hydride, MgH₂, technology behind China's 2025 non-nuclear hydrogen bomb test, is a scientific feat based on a unique thermal decomposition mechanism that generates powerful energy without requiring nuclear reactions. When triggered by a small amount of conventional explosives, MgH₂ undergoes rapid decomposition, releasing hydrogen gas at an impressive rate, reaching 90% within 0.03 seconds. This far surpasses the reaction speed of typical chemical explosives by as much as 30 times. The released hydrogen immediately mixes with the surrounding air, creating a sustained combustion reaction that produces a fireball with a temperature exceeding 1,800 degrees Fahrenheit, with shock waves reaching a maximum pressure of 62 psi at a distance of 6.5 feet from the explosion's center. The physical structure of MgH₂ is the key factor behind its outstanding effectiveness. This material possesses a rutile crystal structure with partially ionic covalent bonds, enabling hydrogen storage at a high volumetric density of up to 7.1 pounds per cubic foot, 3.75 times greater than high-pressure compressed gas cylinders. The decomposition reaction of MgH₂ requires an initial temperature ranging from 570 to 750 degrees Fahrenheit to break the MgH bonds. However, thanks to the so-called burst effect, the activation energy drops significantly to only 0.12 to 1.51 electron volts, allowing the process to occur swiftly and efficiently. This ensures that energy is released evenly, creating an explosion capable of generating extensive thermal impact. with combustion lasting up to 2.5 seconds, considerably longer than traditional explosives like TNT. Another remarkable feature lies in the chemical properties of MgH₂, which allow it to operate without any radioactive materials, making this technology fundamentally different from conventional thermonuclear bombs. The hydrogen-air combustion reaction produces magnesium oxide powder, MgO, as its main byproduct, a stable compound with minimal environmental impact. Scientific studies have also shown that MgH₂ can maintain stability under normal conditions. But when activated, it produces explosive energy at far higher efficiency than other materials, such as cyclotromethylene trinitromine, RDX, due to its high energy density and controllable reaction characteristics. The breakthrough in industrial-scale production of magnesium hydride, MgH₂, has placed China at the forefront of advanced materials technology, especially after the non-nuclear hydrogen bomb test in the year 2025. The world's first MgH₂ production plant was constructed in Yulin, Shanxi Province, and began operations in January of 2025 with an impressive capacity of 165,000 tons per year, equivalent to approximately 330 million pounds. This plant employs the one-pot synthesis method, a groundbreaking technique that enables the hydrogenation of pure magnesium at pressures ranging from 116 to 174 pascal and at a temperature of around 570 degrees Fahrenheit, significantly reducing complex processing steps compared to traditional methods. This process not only enhances efficiency, but also ensures stable production, meeting the growing demand for applications ranging from military systems to clean energy solutions. One of the most remarkable achievements of the Yulin plant is its ability to reduce production costs to approximately $11,300 per ton, a figure up to 99% lower than similar production methods previously tested elsewhere in the world. This was made possible by leveraging the abundant magnesium reserves from China's domestic mines, combined with green hydrogen produced from renewable energy sources, such as solar and wind power in the Northwest region, to ensure safety. The plant is equipped with an oxygen-free production environment, with automated sensors continuously monitoring operations to prevent unwanted reactions caused by the flammability of MgH₂ when exposed to humid air. The technology also incorporates special protective coatings for MgH₂ particles, maintaining stability during storage and transportation. In addition, China is expanding production capacity with plans to construct a new plant in Xinjiang, expected to be completed in the year 2027, with an annual capacity of up to 550,000 tons. This facility, invested by the China State Shipbuilding Corporation, CSSC, with an estimated budget of $170 million, will integrate advanced automation technologies to optimize processes and minimize risks. Improvements such as the use of niobium oxide catalysts and ball milling techniques to create nanoparticles have increased hydrogenation efficiency while reducing the required decomposition temperature to approximately 530 degrees Fahrenheit under certain conditions. These efforts not only reinforce China's leading position, but also lay the foundation for exporting MgH₂ technology to international markets. The military applications of magnesium hydride MgH₂ technology have opened a new chapter in advanced weaponry, harnessing the power of this material to create more efficient and flexible systems, as demonstrated by the non-nuclear hydrogen bomb test in the year 2025. One of the most notable applications is the integration of MgH₂ into torpedoes, extending their range from 31 miles to as much as 75 miles, thanks to the energy released from hydrogen combustion. The post-reaction byproduct, magnesium oxide MgO powder, possesses non-sonar reflective properties, making torpedoes more difficult to detect in underwater operations and providing a significant tactical advantage. Unlike traditional explosives, MgH₂ produces uniform shock waves with a maximum pressure of 62 psi at a distance of 6.5 feet, enabling precise target destruction without the use of radioactive materials. Beyond torpedoes, MgH₂ is also being studied for use in combat drones and precision-guided missiles. Thanks to its compact size and ability to generate powerful explosive energy, this material allows for the design of lighter warheads, reducing overall weapon weight by about 20% compared to systems using conventional explosives like RDX. This is particularly useful in the development of unmanned aerial vehicles capable of carrying larger payloads or operating for longer durations, with flight ranges extended up to 620 miles in certain simulated tests. Furthermore, MgH₂ can be integrated into tactical weapon systems such as guided bombs to generate intense thermal effects, making it highly effective for rapidly destroying concentrated targets, including industrial infrastructure or weapon depots. A key advantage of MgH₂ is its non-nuclear nature, ensuring compliance with the Nuclear Non-Proliferation Treaty, which opens the possibility of exporting this technology to allied nations without international legal barriers. Researchers at Institute 705 have developed sophisticated activation mechanisms using catalysts such as titanium fluoride to control the hydrogen release rate, ensuring safety during operation and storage. With a low production cost of only about $11,300 per ton, MgH₂ delivers superior economic efficiency compared to traditional thermobaric explosives, which typically cost 5 to 10 times more for the same mass. The magnesium hydride MgH₂ technology not only marks a breakthrough in the military field, but also unlocks vast potential in civilian applications, particularly in clean energy and infrastructure development in China. One of the most remarkable achievements is the integration of MgH₂ into hydrogen storage tanks for electric vehicles. With an exceptional storage capacity of about 7.1 pounds of hydrogen per cubic foot, 4 times greater than high-pressure tanks used in models such as the Toyota Mirai. This allows hydrogen-powered vehicles to achieve a driving range of up to 750 miles with a single refueling that takes only 3 minutes, offering performance far beyond current lithium-ion battery systems in terms of refueling speed and travel distance. In the field of clean energy, MgH₂ plays a crucial role in reducing the cost of green hydrogen production to just $1.8 per kilogram, significantly lower than the $4.5 per kilogram typical of conventional methods. The technology is being applied in large-scale infrastructure projects in China, most notably the hydrogen production plant in Xinjiang, with an annual capacity of 110,000 tons. Powered entirely by solar energy from renewable farms spanning 12,000 acres in the Gobi Desert. This project not only supplies clean fuel for transportation, but also supports heavy industries such as steel and cement production, cutting carbon emissions by 2 million tons per year. Another notable project is the Ningxia Baofeng Energy Complex, where MgH₂ is used to store hydrogen for trains and heavy-duty trucks, supported by a refueling system capable of serving 200 vehicles per day, equivalent to 44,000 pounds of hydrogen. In addition, MgH₂ has been applied in other high-tech fields, such as improving anode materials for lithium-ion batteries, increasing energy density by 15% compared to conventional materials. The technology also appears in advanced hydrogen transport systems, such as Hydrexia's trailers, which can store 2,200 pounds of hydrogen at ambient temperature and pressure, reducing transportation costs to just $0.3 per kilogram compared to $1.2 for liquid hydrogen methods. These projects are backed by massive clean energy infrastructure investments, estimated at $71 billion by the year 2030, with over 40% directed toward hydrogen-related technologies. These advances not only strengthen China's leadership in renewable energy, but also create a sustainable infrastructure model that could be replicated globally. The international response to China's magnesium hydride MgH₂ technology and its non-nuclear hydrogen bomb test in April 2025 highlighted the outstanding potential of this material in science and industry, sparking excitement about its innovative applications. Global scientists, particularly in the field of materials chemistry, praised MgH₂'s solid hydrogen storage capability, reaching a density of 7.1 pounds per cubic foot, far surpassing compressed gas at 2.8 pounds per cubic foot and liquid hydrogen at 4.4 pounds per cubic foot. At the International Energy Conference in 2025, experts noted that MgH₂ could reduce hydrogen storage costs to as low as $0.5 per pound, compared to $2 per pound for current technologies, opening promising prospects for the global clean energy market, which the International Energy Agency IEA projects will triple by 2030. In the industrial sector, major corporations in Japan and Europe including leading automakers, are actively exploring the integration of MgH₂ into hydrogen fuel systems. A report from the Technology Exhibition in Frankfurt in 2025 revealed that these companies are negotiating with China to deploy 50 MgH₂-based hydrogen refueling stations across Europe by 2029, each capable of supplying 22,000 pounds of hydrogen per day for electric vehicles and heavy-duty trucks. MgH₂'s cost advantage around $11,300 per ton compared to millions of USD for other hydride materials has attracted attention from emerging markets such as Southeast Asia and Africa, where the demand for clean energy is rapidly increasing. Pilot projects in Southeast Asia have also begun applying MgH₂ to hydrogen transport systems, such as trailers capable of storing 2,200 pounds of hydrogen at ambient conditions, reducing transport costs to just $0.3 per pound. The scientific community has also praised the versatility of MgH₂, not only in energy, but also in other industrial applications. For example, the material is being researched for improving lithium-ion battery anodes, increasing energy density by 15% compared to conventional materials, which could enhance the performance of electronic devices and electric vehicles. Discussions at the Technology Symposium in Tokyo in 2025 emphasized that China's MgH₂ technology could become the new global standard for hydrogen storage, thanks to its scalability and low cost. This recognition reaffirms China's leadership in advanced materials, while raising a broader question: how will MgH₂ technology shape the future of the world? Magnesium hydride, MgH₂, first introduced through China's non-nuclear hydrogen bomb test in 2025, is opening a promising future for both advanced technology and sustainable energy, with China taking the lead in this revolution. In the military field, MgH₂ has the potential to be integrated into next-generation space and naval weapon systems. Military satellites powered by solid hydrogen fuel could reach low Earth orbit with payloads increased by 25% compared to current systems. Unmanned submarines could also harness MgH₂ to extend underwater operations up to 30 days, thanks to more efficient energy storage that reduces the need for refueling compared to traditional battery systems. These advancements, with operating costs as low as $0.4 per pound of hydrogen energy, deliver unprecedented advantages in both performance and economics. In the energy sector, MgH₂ is reshaping the global hydrogen industry, with the market projected to reach $1.5 trillion by 2032, in which China is expected to account for 40% of global green hydrogen output. Pilot projects in China, such as hydrogen storage systems for smart cities in Shenzhen, use MgH₂ to power urban grids, achieving energy conversion efficiency up to 85%, which is 20% higher than compressed gas systems. In addition, China is deploying mobile hydrogen power stations in rural areas, each capable of supplying electricity for 5,000 households, with operating costs of only $0.2 per kilowatt hour, significantly lower than coal-based electricity. On the international cooperation front, China is leading initiatives within the International Hydrogen and Fuel Cell Association, IHFCA, with plans to export MgH₂ technology to Southeast Asia and Africa. A standout example is its partnership with Indonesia, which aims to build 10 MgH₂-based hydrogen plants by 2030. Each plant will produce 55,000 tons of hydrogen annually, enough to fuel 1.2 million electric vehicles. These projects not only boost economic growth, but also cut carbon emissions by 1.5 million tons annually in the region. In transportation, MgH₂-powered hydrogen trains in China have already reached maximum speeds of 125 miles per hour, with operating costs reduced by 30% compared to diesel trains, paving the way for a zero-emission rail network. These advancements not only reinforce China's leadership in materials technology, but also shape a future where clean energy and advanced military applications coexist in balance. With mass production capacity for MgH₂ and large-scale infrastructure projects underway, China is laying the foundation for a more sustainable world, one where this technology could become the new standard for both energy and global security. So what do you think? Could MgH₂ truly become the new standard for global energy? Which industry do you think this technology will transform next? Share your thoughts in the comments below. And don't forget to hit subscribe so you won't miss the latest insights on technology, national strategy, and groundbreaking innovations shaping our future. Top 10 Discoveries Official will be back with untold stories, projects that challenge limits, and quiet revolutions making waves across the globe. See you in the next video.